Now here we are going to discuss about the circular motion in a vertical plane. So we have a body of mass m attached to a string, and we roll it around in a vertical plane. So the tangential velocity will not be constant, tangential speed will not be constant. At the lower point, the tangential speed will be greater, and at the highest point, the tangential speed will be the least. Now, in the first, we are going to attempt to get the expression for the tension of the string at every single point. So here we have the circular path. Here we have the diametric vertical diameter. Let us assume that the body is moving in anti-clockwise direction over the circular path. Let us mark this point at the center approximately. Now, let's assume that this is the lowest point, so the body is here. This is how it looks, and this is the highest point when the body is here. The mass of the body we can write as m. And we can name this point A. We can name this point B. Now we will choose a random point here when the body is here. Alright, here is the same body. We can draw the radius vector to that point. Let us assume that the vertical angle at this point, random point Z, is, let's mark it as theta. So this, we name this point as C. Now, this is the string. You can see that OC, in this figure, OC is the string, and this is the radius vector as well. So this distance OA is R, OB is also equal to R. Now, there are two forces acting on the body. Let's show them. Here we have the weight of the body acting downward. This is acting downward. Let's mark it as W. That is W. That is equal to mg. And in this case, we have the tension on the string acting along the string, away from the body. Here we have the tension because the name of the point is C, so we call the tension of the string is TC. Now, the TC should provide centripetal force, and it should also compensate the component of the weight acting along the radius vector. So let us mark the component of the weight acting along the radius vector. Here is the component of the weight acting along the radius vector. So we can see that if this vertical angle is theta, this will also be theta. So this component of the weight acting along here will be mg cos theta at any point. Now we can write the tension should provide the FCP, the centripetal force, that is given by mvc squared over r, plus it should balance the component of the weight acting along the radius vector outward. So you can just write this as mg cos theta. This is the general expression for the tension at any point on the string. I will take the specific cases for tensions at A and B. So let us start with tension at A. Okay, here I will write it. Tension, okay, I can do it even here. Let's see. Let's do it in another color. Tension at point A. What will be the tension on the string at point A? We'll try to work it out. So at this point, we can substitute the values for the angle, and you will get it right. Look at the equation earlier we had. TC is equal to MBC squared over R plus mg cos theta. So here, in this case, at tension at A, in this case, we can say that theta will be 0. So you can write TA is equals to M, instead of VC, we should write VA. So MVA square over R plus mg cos 0. Cos 0 is equal to 1. So you will get tension at the lowest point, TA, is equal to VA square over R plus, you will get mg cos 0. Cos 0 is 1, so this is mg. So this is the expression for the tension when the body is at A. I use the same equation and we can work out the tension when the body is at B. So I will write it here. Tension on the string, so put it as equation number 2 or 3, something like that. Tension at B. So look at the equation again. This is the expression. T is equals to mv square over R plus mg cos theta. So we use the same equation. Instead of C, we will write B. That's the only difference. But in this case, theta would be, because you are moving the body all the way to the top. When you move the body all the way to the top, here the vertical angle becomes 180 degrees. So theta in this case will be 180 degree, and the expression we get TB equals to the centripetal force there, that is mVB square over R plus mg cos 180 degrees. Cos 180 is minus 1, this becomes negative mg in that case. So you will get TB is equals to mVB square over R minus mg. This is the expression for the tension when the body is at the point B. Now let us take a special case. Suppose the body just manages to cross over instead of falling, because if the centripetal force, if the speed is not sufficiently high, the body will not be able to complete the circular motion. In that case, the body will fall right back to the center, because there is not enough speed to keep the body moving in a circle. That's the idea. So let us assume that we have just enough force to keep the body moving in a circle. So the tension of the string at this point would become 0. So we can just write, let us see, what will be T. Here you can see that it's a special case when the VB is minimum. In such case, when VB is minimum, what would happen? TB is equal to 0. Then you will get mVB square over R is equal to mg. So that will be the special equation, and from here you can see something more interesting. VB will be root RG. This is the minimum velocity at the top to keep the body moving in a circular path. What is this? This is the minimum velocity at the top to keep the body moving in a circular path. This is actually we can write it down here, minimum velocity or minimum tangential speed to keep the body moving in a circle. of course, at the point B or at the top. All right, at the top. So this condition we will come back again. That's an interesting result we have. So these are the topics that we have covered in this lesson.